Okay, so now let me let me provide a proposition which will be useful to prove first welfare theorem. Okay, so okay, consider the following utility maximization problem. Okay, and suppose x star y star solves this problem. Okay, then the following is true. Okay, first, if utility from bundle x prime y prime is strictly greater than utility from bundle x star y star, then the expenditure required to purchase x prime y prime must be bigger than m. Is this true? Why do you think this is true? Because x star y star is a utility maximization solution to the utility. It may not be unique, I mean, that is not what I'm saying. So if x star y star is a solution to the utility maximization problem, then any bundle that gives you higher satisfaction level than x star y star must not be affordable, because otherwise you would not have chosen x star y star, you would have chosen something else. So something that is affordable, cannot give you higher utility than your chosen bundle, right? So if something gives you strictly higher satisfaction level than your chosen bundle, because that's what is utility maximizing, then it must be the case that the expenditure required on that particular bundle must be strictly greater than m, right? Okay, so this is something which is kind of obvious, that this is true. Okay, the second thing is, if u is increasing and okay, then the expenditure required to purchase x prime y prime must be greater than or equal to m. Okay, so this is the second proposition, and this particular proposition requires u to be increasing, because if u is not increasing, then this may not hold. Okay, can you think of an example? Can you think of an example where u is not increasing and this holds but this does not hold? Okay, so for u equal to 0, you can consider some set of positive prices and some positive amount of income. Okay, let's say prices are 1 1, income is 1. Okay, and notice that a bundle, every bundle is utility maximizing, so you can just consider maybe 1 0. Okay, so notice that 1 0 is utility maximizing, and utility from 0 0 is also greater than or equal to utility from 1 0, right? Utility from 0 0 is greater than or equal to utility from 1 0, but the expenditure required on 0 0 is less than 1, right? Yes or no? So this is not true when u is not increasing. Okay, so let us show that this is true when u is increasing. Okay, so this is how we are going to prove it. Suppose u is increasing and ux prime y prime is greater than or equal to ux star y star. Okay, and by way of contradiction, and let us suppose that px x prime plus py y prime is strictly less than m. Okay, so we will arrive at some contradiction. So if we assume this, if you assume that this is not true, then we'll arrive at some kind of a contradiction. Okay, so we'll try and arrive at that contradiction. Okay, so suppose u is increasing and utility from x prime y prime is greater than or equal to utility from x star y star, which is x utility maximizing choice. Okay, and the expenditure required to purchase x prime y prime is strictly less than m. Okay, so let's define epsilon to be the remaining amount. Okay, and let us distribute this remaining amount on buying x and y equal amounts. Okay, and try to increase this bundle x prime y prime. So now consider a new bundle x prime plus epsilon by 2px comma y prime plus epsilon by 2py. Now, can you tell me what is the utility if you compare utility of these two bundles? Which one is bigger? The new bundle. That's right. This is the one which is bigger. And I know that this is greater than or equal to u x star y star. Now what I'm going to do is I'm going to just show that this is also affordable. Okay, I'm also going to show that this is affordable. So how do I show that? Let's figure out what is the expenditure. What is the expenditure on this bundle? It is px x prime plus py y prime plus px into this, which is epsilon by 2, plus py into this, which is epsilon by 2, which is px x prime plus py y prime plus epsilon. And what is epsilon? Epsilon is this. So what are we going to get? It is equal to m, right? Because once you're going to replace epsilon by this, you're going to get m. So notice that this bundle satisfies the budget constraint. Now this bundle is affordable and gives you strictly higher satisfaction level than this bundle, the chosen bundle. Isn't that a contradiction? Because this was utility maximizing. This bundle was utility maximizing. Then how can it give you lower satisfaction level than another affordable bundle? It cannot, right? So this is a contradiction. Is that fine? Okay, so we have found a bundle which offers higher utility than X star Y star and is also affordable. Is that clear? Okay, so this is a contradiction that that we were trying to arrive at. So basically, if we assume that U is increasing and a bundle gives you at least as much satisfaction level as the chosen bundle, and we also assume that it costs strictly less than M, then we'll arrive at a contradiction. So that means if we suppose this, then we'll arrive at a contradiction. So therefore, this is not true. That means we have shown that it must be the case that the expenditure required on buying such a bundle, such an X prime Y prime bundle, must be greater than or equal to M. Is that okay? Okay, so please note this down. This is something which will be needing. So I'll come back to this. When I'll be proving the first welfare theorem. Okay, so first I'll state the first welfare theorem and then I'll prove it. Okay, and for that I'll be needing this particular result. Okay, so please note that both the aspects are important. The first is that if any bundle gives you strictly higher satisfaction level than the then your utility maximizing choice, okay, then your chosen bundle, let's call that the chosen bundle, then it must cost strictly more than M. So then it must not satisfy the budget constraint. Obviously that's true. And the second condition, the second thing that is true, the second proposition that is true is that if utility is increasing and there is any other bundle X prime Y prime that gives you at least as much satisfaction level as the chosen bundle, then it must cost at least as much as M. So these are the two things which we'll be needing. Okay, is that okay? Okay, so here is the first welfare theorem. So what I'll do is I'll write and prove this proposition for two consumers, two goods economy. But this proposition also holds for any number of consumers and any number of goods. Okay, as long as the setup is similar. That means utility is increasing. And the commodity space is RL plus. For each individual. Uh, you know, and uh, and there are L goods, M consumers, so it's the exact result also holds for any number of consumers and any number of goods, and the proof is exactly the same. Okay, and I'm writing it for two consumer two goods because it saves some space and it keeps the notation simple. So I'll just use the same notation that you have seen, which is x1 y1 x2 y2 for the bundle, rather than introducing a new notation for n consumers L goods. But if you are interested, you can just write the proof exactly like this for any number of consumers and any number of goods. Okay, so here is the first welfare theorem. If u1 and u2 are increasing, so we are talking about an exchange economy. Okay, then this economy satisfy the first welfare property. Okay, this is the first welfare theorem. So all that you have to do is you just have to show that if you have an exchange economy where u1 and u2 are increasing, okay, then every competitive equilibrium of that economy is Pareto efficient. Is that okay? Okay, so this is what we are going to prove. So here is the proof. So the way we are going to prove this is as follows, so let me first give you the idea that this is the line of reasoning that we are going to use to prove it. So what we are going to do is, basically this is what we want to show, that every competitive equilibrium, so if this is set of competitive equilibrium allocations and this is set of Pareto efficient allocations, I want to show that CE is a subset of PE. Okay, if this is a set of competitive equilibrium allocations and this is a subset of Pareto efficient allocation, I want to show that every competitive equilibrium allocation is Pareto efficient, right? This is what I want to show. Yes or no? Okay, so the way we are going to show it as follows, we are going to just pick an allocation from the competitive equilibrium set of competitive equilibrium allocations, and so what we'll do is consider, so this is a line of reasoning. I'm going to erase this and write it properly, but so we'll start with this, that consider A in CE, and suppose that A does not belong to PE. So this is my basically assumption that, okay, fine, let's assume that A is not in PE, and this should lead to some contradiction. So this is basically the way we are going to prove it. Okay, so let's prove it. Okay, suppose x1 star, y1 star, x2 star, y2 star is a competitive equilibrium allocation supported by prices px star, py star, and let us assume that it is not Pareto efficient. Okay, so suppose x1 star, y1 star, x2 star, y2 star is a competitive equilibrium allocation supported by prices px star, py star, and let us suppose that it is not Pareto efficient. Okay, now we are going to proceed in this direction and we'll arrive at some kind of a contradiction. Okay, and that would mean that these two things cannot happen together. That means this way of going forward would lead to something wrong, and therefore these two things cannot happen together, and therefore every competitive equilibrium must be Pareto efficient. Okay, so this is basically the way we want to proceed and answer this. Okay, so if this allocation is not Pareto efficient, then what must be true? There exists a feasible allocation which is Pareto superior to it, right? Basically, for both individuals, this is true, and for at least one individual, this is true. Yes or no? Do you agree? Is this clear so far? The argument is clear. We are just saying that because this, let's call this star allocation, let's call this prime allocation. We are just saying because star allocation is not Pareto efficient, so there must be some prime allocation which is Pareto superior to it. So this is what it means by Pareto superiority, right? And this prime allocation must also be feasible. Okay. Now, notice that U1 and U2 are increasing. So if a bundle gives you at least as much satisfaction level as this bundle, this is your chosen bundle, right? When these are the prices, this is what you chose, right? Yes or no? Because this is a competitive equilibrium. So if a certain bundle gives you at least as much satisfaction level as the chosen bundle, then what must be true? Must be greater than or equal to the value of the endowment, right? Because that's the income, right? Yes or no? We have just proved it. Remember the proposition that we just proved? And this is true for both the individuals. Now, what about this? If for at least one of them, it is the case that xi prime yi prime gives you strictly higher satisfaction level than xi star yi star, then it must be the case that xi prime yi prime must not be affordable, right? At px star py star, right? So I know that this expenditure on the prime bundle is at least as much as at least as much as the value of the endowment for both the individuals, and for at least one of the individuals, it is strictly higher than the value of the endowment. Is that okay? Yes or no? For both the individuals, it is at least as big as the value of the endowment, and for at least one of them, it is strictly higher. Now, if I add them up, suppose I add this, tell me what am I going to get? This, compare these two. If I add them up, now if I want to compare these two, notice that this is greater than or equal to this is greater than or equal to this, and at least one of them is strict. So either this is strictly greater than this, or this is strictly greater than this, or both. So if I add them up, what am I going to get? What can you say about the left hand side compared to the right hand side? Do I get a strict? Yeah, absolutely. Left hand side is strictly bigger, right? Because one of them is strict, right? So at least one of them is strict. So if you are adding them up, both of them are at least weak, and at least one of them is strict. Then obviously you're going to get a strict inequality, right? Now let's look at this. This is actually kind of a contradiction because Because what is this? So if I collect these terms, let's collect these terms over again. Px star x1 prime plus x2 prime plus py star y1 prime plus y2 prime is strictly greater than px star omega 1x plus omega 2x plus py star omega 1y plus omega 2y. Remember that this prime allocation was feasible, right? So if this prime allocation was feasible, what is this? These two are equal, right? And what is this? These two are equal. But if this is equal to this is equal to this, how can this be strictly bigger than this? That's a contradiction, right? Okay, using feasibility of x1 prime, y1 prime, x2 prime, y2 prime, we get that this is strictly greater than this. So a number is strictly greater than itself, which is a contradiction. Is that okay? It's a very nice result, right? So if there are if in an economy, so this is a sufficient condition. Please note that I'm telling you that this is a sufficient condition because you can find examples where u1 and u2 are not increasing, but still first welfare property holds. Okay, so if u1 and u2 are increasing, then definitely every competitive equilibrium is Pareto efficient. But if that is not the case, then it may or may not be. Okay, so if you want to check for the first welfare property, then if you can deduce that, okay, if you can figure out that, okay, fine, u1 and u2 are increasing, then you don't need to check anything. You can straight away say that by this particular result that every competitive equilibrium will be Pareto efficient, because you don't have to now find competitive equilibrium and verify that it is a subset of Pareto efficient allocations, because this particular argument just proves that whenever u1 and u2 are increasing, then in that particular economy first welfare property holds. Okay, so you can just straight away say that every competitive economy is Pareto efficient in that particular economy. But if u1 and u2 are not increasing, then in that case you'll have to do by first principles. You have to first find a set of all competitive equilibrium in that particular economy, then check if it is a subset of Pareto efficient allocations or not. Okay.